students. In this video we are going to discuss about the special type of motion called as rolling motion. Up to this video we discuss linear motion separately, circular motion as well as rotational motion separately. But in some cases body have two or more types of motion, that means linear, circular or rotational combinedly. Then such motion we are going to discuss in this video. If body possesses translational motion or linear motion as well as rotational motion, then the resultant motion of the body is nothing but a rolling motion. For example, if you consider the front wheel of the vehicle or rear wheel of the vehicle, then that rotate about the axis and as well as it transfer or displace from one place to another place. Okay, then there is a translational motion as well as rotational motion also. Then that combination of both motion is a rolling motion. Or if you consider rolling down of an object over the inclined plane, then that motion is the best example of rolling motion. In that case, object transfer from highest level to the lowest level as well as it rotate about some fixed axis. Then the resultant motion of that particular case is nothing but a rolling motion. If we have considered the kinetic energy of that resultant motion or a rolling motion, then that kinetic energy of rolling motion is the combination of translational kinetic energy and rotational kinetic energy. When we have the expression for translational kinetic energy is 1/2 mv square and the rotational kinetic energy is 1/2 I omega square, which is recently derived. Okay, now let us derive the relation or let us derive the equation for kinetic energy of rolling motion. We know that rolling motion is the combination of translational motion and rotational motion. Okay, rolling motion is the combination of translational motion as well as rotational motion. Hence, kinetic energy of rolling motion is also equals to kinetic energy of translational motion plus kinetic energy of rotational motion. Okay, kinetic energy of rolling motion is equal to kinetic energy of translational motion plus kinetic energy of rolling motion. Suppose we consider an object. This is the object having radius r. Displaced from point A to point B linearly with velocity v by performing rotations with angular velocity omega. Okay, then that object have translational kinetic energy as well as rotational kinetic energy, and the combination of both energies is nothing but kinetic energy of rolling motion. Okay, now the translational kinetic energy is 1/2 mv square, where m is the mass of object and v is the velocity with which it is translate from one place to the another place. As well as rotational kinetic energy is 1/2 I omega square, where I is the moment of inertia about this fixed axis and omega is the angular velocity with which object is rotating. Okay, and if we put that two energies in this equation, then kinetic energy, let us consider the symbol for this E. Kinetic energy of rolling motion E is equal to kinetic energy of translational motion, which is nothing but 1/2 mv square plus kinetic energy of rotational motion, which is 1/2 I omega square. Okay, but I is equal to mk square. We have the relation I is equal to mk square, where k is the radius of gyration about the given axis and V is equal to R omega, that gives omega is equal to V by R. And if we put these two values in this equation, then we get kinetic energy of rolling motion E is equal to 1 by 2 m v square plus 1 by 2 I is replaced by mk square, and omega square is v square by r square. Sorry, capital R, because radius of that object is we consider capital R, in v square by r square. Now in this two term we have the common factors 1 by 2 m v square, 1 by 2 m v square. Let's take common. Then E is equal to 1 by 2 m v square plus, in bracket 1 plus k square by r square. And this is the equation for kinetic energy of rolling motion, but in terms of linear velocity v. Kinetic energy of rolling motion in terms of linear velocity v. We get the same equation in terms of angular velocity also, but for that we have to put v is equal to r omega in the first term. V is equal to r omega in the first term. Let us do that. Before that, note down this by taking a screenshot or by pausing the video. This is the expression for kinetic energy of rolling motion in terms of linear velocity. Now we are going to derive the expression for kinetic energy of rolling motion in terms of angular velocity. From this equation, E is equal to, suppose here is equation number 1. From equation 1, E is equal to 1 by 2 m v square. In the place of v square, we have to put r omega square, 1 by 2 m r square omega square. Okay. Plus, here 1 by 2 in the place of I, mk square and omega square as it is. Now by taking common 1 by 2 m omega square in bracket r square plus k square. This is the expression for kinetic energy of rolling motion in terms of angular velocity. Okay, very simple type of motion, rolling motion. If body possesses both the types of motion, that means translational motion as well as rotational motion, then the resultant motion of that body is nothing but a rolling motion. And the kinetic energy of rolling motion is the combination of kinetic energy of translational motion and kinetic energy of rotational motion. Kinetic energy of translational motion is given by 1 by 2 m v square, and kinetic energy of rotational motion is given by 1 by 2 I omega square. Put that values in this equation and we get the equation E is equal to 1 by 2 m v square plus 1 by 2 I omega square. In the place of I, we can put m k square, where k is the radius of gyration, and at the place of omega we can put v by r, or omega can be replaced by v by r by the relation v is equal to r omega. By putting that values of I and omega in the equation 1, we get the equation E is equal to 1 by 2 m v square plus 1 by 2 m k square into v square by r square. Now by taking common as 1 by 2 m v square, in bracket we have 1 plus k square by r square, and this is the expression for kinetic energy of rolling motion in terms of linear velocity. We can obtain same equation in terms of angular velocity also. For that, in the equation 1, we have to put the value of v is equal to r omega. We can replace v by r omega, and by simplifying and by taking common 1 by 2 m omega square, we get the equation E is equal to 1 by 2 m omega square r square plus k square. This is the equation for kinetic energy of rolling motion in terms of angular velocity. We have to discuss about the linear velocity or speed and acceleration while you are rolling down an inclined plane. Okay, you have to find the expression for linear velocity of an object and linear acceleration of an object if object is rolling down over the inclined plane in this point. Okay, for that, Consider an object of mass m and radius r rolling down over an inclined plane of angle of inclination theta. Theta is the angle of inclination. In that rolling motion, object covers a total distance s. The height of an object is h. These are the considerations. Now, at the topmost position, the total energy of an object is total energy at the top. Total energy at the top is equal to kinetic energy plus potential energy. But if we consider the object is rest at the top, then that kinetic energy is 0 and object is at height h from the horizontal surface, hence its potential energy is mgh. Okay, this is the energy at the topmost position. At the lowermost position, total energy at lower position is equal to kinetic energy. Obviously, the kinetic energy is nothing but a kinetic energy of rolling motion because object is rolls down from this point to this point. Kinetic energy of rolling motion plus potential energy. But at the lowest position, height is 0 because of that potential energy is also 0. And total energy at lower position is equal to kinetic energy of rolling motion, which is nothing but 1 by 2 mv square 1 plus k square by r square. Okay, these are the two energies. Total energy at topmost position, total energy at lowermost position. At the topmost position, object have only the gravitational potential energy because object is considered to be rest at the topmost position. When we release that object, then that object performs rolling motion and rolls down towards the horizontal position, and the lowermost position, the potential energy becomes 0 and kinetic energy is nothing but a kinetic energy of rolling motion. In this process, or in this case, gravitational potential energy is fully converted to kinetic energy of rolling motion by the law of conservation of energy, and we can write gravitational potential energy at top is equal gravitational potential energy at top is equal to kinetic energy of rolling motion. Okay, by the law of conservation of energy. How this equation becomes? By the law of conservation of potential energy, by the law of conservation of energy, we can write kinetic energy at topmost position is equal to kinetic energy at lowest position. Okay, but kinetic energy at topmost position is only gravitational potential energy, and kinetic energy of lower position is only kinetic energy of rolling motion. Hence, we can write gravitational potential energy at the top is equal to kinetic energy of rolling motion at the bottom, at the lowest position, and that gravitational potential energy becomes mgh, and the kinetic energy of rolling motion is 1 by 2 m v square 1 plus k square by r square. One plus k square by r square. In this equation, m and m get cancelled, and v square is equal to twice gh upon 1 plus k square by r square. Twice gh upon 1 plus k square by r square. If we are taking a square root on both sides, then equation becomes v is equal to square root of twice gh upon 1 plus k square by r square, and this is the expression for linear velocity of an object which is rolling down over the inclined plane, or linear velocity while pure rolling down. Pure means without friction. Object is rolling down without friction. Okay, this is the expression for linear velocity of rolling motion. let us come towards the linear acceleration. I modified the diagram. For the motion of an object from top to bottom, object covers a distance s. Object covers a distance s. Initially, its velocity is 0. And with the velocity v, it travels towards the lowermost position. And consider the acceleration is a. A. What we have? S. Distance covered from top to the bottom. U is initial velocity. Which is 0. A is the acceleration with which object rolls down from top to the bottom. And V is the linear velocity. Or we can say that final velocity also. Initial velocity is 0. Final velocity is 0. And we have the third kinematical equation. V square is equal to V square plus twice AS. V square is equal to U square plus twice AS. Before that, we have the equation for V is equal to under root twice GH 1 plus K square by R square. This is the expression for V which we have. Okay. Now put that all values in this equation. Third kinematical equation is V square is equal to V square plus twice AS. But initially object is at rest because its initial velocity U is equal to 0. But U is equal to 0. Then we get the equation V square is equal to twice AS and A is equal to V square upon twice S. A is equal to V square by twice S. And if we consider a figure, then what is H? V square is equal to twice S. This equation. A is equal to V square by twice S. Then from figure, H is equal to, if this angle is theta, then that H is equal to S sin theta. H become S sin theta and S is equal to H upon sin theta. Put this value of S in this equation, we get A is equal to V square sin theta upon twice H. At the place of S, we put H upon sin theta. By putting the value of S, we get A is equal to acceleration. A is equal to V square sin theta upon twice GH. But what is V? But V is equal to under twice GH upon 1 plus K square by R square. 1 plus K square by I square. And V square is equal to twice GH 1 plus K square by I square. Put this value of V square in above equation. We will get linear acceleration A is equal to V square twice GH upon 1 plus K square by R square into sin theta upon twice H. Twice H get cancelled. And linear acceleration while pure rolling or linear acceleration in rolling motion E is equal to G sin theta upon 1 plus K square by R square. And we get the relation or we get the equation for linear acceleration of rolling motion or linear acceleration while pure rolling down over an inclined plane.